The main theme of this paragraph is spacecraft propulsion and the various methods used to accelerate spacecraft in the vacuum of space. It highlights the different propulsion systems used for in-space propulsion and the advantages and drawbacks of each method. The paragraph also discusses the importance of developing hypothetical in-space propulsion technologies for future space exploration and the need for a portfolio of propulsion technologies for optimum solutions to a variety of missions and destinations. The purpose of a propulsion system in space is to change the velocity of a spacecraft, and designers measure spacecraft performance in terms of specific impulse. Any additional impulse, no matter how small, can result in a change in the orbit path. Therefore, it is essential to choose the right method of acceleration, depending on the objective of the mission. The theme of this passage is propulsion systems for human spaceflight and the importance of reaction mass and energy. The author explains how Earth's gravity affects human space travel and how an ideal propulsion system would provide continuous acceleration to counteract the negative effects of free fall. The use of reaction mass is key to changing the momentum of a spacecraft, and designers must focus on effectively using it to achieve specific impulse. However, high mass-efficient engines require enormous amounts of energy per second to produce high thrusts, leading to lower thrust and reduced energy efficiency. Different propulsion methods such as burning fuel or using electrically accelerated ions are described. The author urges a closer examination of the balance between mass efficiency and energy efficiency in propulsion design. The development of technologies in the technology area, TA, holds immense potential for groundbreaking breakthroughs that can transform space exploration. However, there is not a single propulsion technology that would benefit all mission and mission types, given the unique and varied requirements for in-space propulsion. The technology should support various applications, from small satellites and robotic deep space exploration to space stations and human missions to Mars. Mission pull characterizes technology that is necessary to meet a planned NASA mission requirement, while technology push encompasses any other relationship between technology and mission. In addition, a space demonstration is the spaceflight of a scaled version of particular technology or critical technology subsystem, while validation flight serves as a qualification flight for future mission implementation. Various spacecraft operate in different space regions, including orbital maneuvering, interplanetary travel, and interstellar travel. Artificial satellites are typically launched into the desired altitude by conventional liquid or solid propelled rockets, but they require onboard propulsion systems for orbital station keeping and attitude control so that they remain correctly pointed with respect to the Earth, the Sun, and outer space's objects of interest. Satellites are also vulnerable to drag from the atmosphere, and they may require orbital station keeping to remain in orbit over an extended period. While many satellites need to change orbits from time to time, they become useless once their ability to adjust their course is depleted. For interplanetary travel, spacecraft use their engines to leave Earth's orbit. Initial boost from the rocket, gravity slingshot, monopropellant/bipropellant attitude control propulsion system, can also facilitate exploration within the solar system. The spacecraft then makes its way to the intended destination through a series of short-term trajectory adjustments between which the spacecraft moves without accelerating. Fuel efficiency can be maintained through a home and transfer orbit to move between two circular orbits. The spacecraft begins in a roughly circular orbit around the Sun and requires a short period of thrust to accelerate or decelerate it into an elliptical orbit, tangential to the previous orbit and the orbit of the destination. The spacecraft freely falls along this elliptical orbit until it reaches the destination. Special methods like aerobraking or aerocapture may be employed to make the final orbital adjustment. The possibility of interstellar travel within a human's lifetime is still a distant dream due to the humongous distances involved. However, the hope for it is alive, and various hypothetical designs have been discussed. The main challenge remains acquiring enough velocity during launch and coming to a halt on arrival. There are 4 primary technology categories based on the propulsion system and technical maturity: chemical, electric, advanced, and supporting technologies. Chemical rocket engines, which derive the needed thrust from chemical reactions, are widely used, with hydrazine being the most common propellant used to date. However, due to its high toxicity, which puts human life at risk. It may soon be outlawed across Europe. The development of safe and environmentally friendly alternatives like nitrous oxide-based engines has garnered a lot of traction, with several commercial companies working on it. Rocket engines' high specific power and thrust make them the most suitable engine for propelling spacecraft. The theme of the story is about different types of rocket engines used for space missions. The use of electric propulsion is highlighted due to its high specific impulse but low values of thrust, making it suitable for station keeping on commercial satellites and certain space missions. Compared to conventional rocket engines, electric propulsion uses electrostatic or electromagnetic forces to accelerate the reaction mass directly, ionizing atoms to create a voltage gradient. This idea dates back as early as 1906 but has been refined over the years. The Glenn Research Center is currently working on developing primary propulsion technologies that reduce cost, mass, and travel time by using electric propulsion systems like ion and Hall thrusters, as well as combining them with solar sails. Besides electric propulsion, nuclear energy may be necessary for missions further out or at higher power. It is important to note that the maximum amount of thrust that can be produced by any source of electrical power is limited by the amount of power generated and the weight of the power source, ultimately affecting the performance of the spacecraft. Different types of thrusters like ion, electrothermal, and electromagnetic are currently being used to accelerate ions and generate plasma to increase the heat of the bulk propellant. The theme of this paragraph is about field propulsion methods in space exploration that do not rely on reaction mass. Although the law of conservation of momentum suggests that an engine without a reaction mass cannot accelerate the center of mass of a spaceship, space is not empty and contains fields and waves that can impart momentum to a craft. This fact is utilized by different space drives, such as tether propulsion, solar sails, magnetic sails, mag sails, mini-magnetospheric plasma propulsion systems, and e-sails. These propulsion structures need to be proportionally large due to the diffuse nature of these phenomena. Different projects, such as NanoSail D, Sunjammer, CubeSail, and Icaros, have demonstrated the effectiveness of these field propulsion methods. The theme of the story is the need for advanced propulsion technologies in order to facilitate human and robotic exploration of the solar system. The current state-of-the-art in propulsion is limited by conventional chemical rockets, which are not sufficient for missions to the most distant planets in a reasonable amount of time. In order to overcome this problem, more efficient in-space propulsion technologies are required. Various hypothetical propulsion techniques have been proposed, but many are considered highly speculative and not yet feasible. A summary of proven technologies is provided, along with their characteristics such as the effective exhaust velocity, typical amounts of thrust and burn times, and maximum delta V. It is clear that in order to overcome the challenges of time and distance in space exploration, more advanced propulsion systems are necessary. The theme of this article is exploring various launch assist mechanisms and propulsion systems for space travel. The article mentions famous static test locations at rocket ground test facilities, but acknowledges that some systems cannot be adequately tested on the ground and require test launches at a rocket launch site. The article goes on to list proposed non-rocket space launch assist mechanisms, including the skyhook, space elevator, launch loop, space fountain, and orbital ring. The article also discusses the efficacy of air-breathing engines and conventional air-breathing engines such as ramjets or turbojets, which are too heavy for a launch vehicle. However, air launching from separate lift vehicles or using jet engines mounted on a launch rail could be feasible options. The article concludes by mentioning the use of planetary atmospheres and surfaces for spacecraft velocity adjustments. Aerobraking is a method that reduces the high point of an elliptical orbit by repeated brushes with the atmosphere at the low point of the orbit, saving fuel and avoiding the need for a heat shield. This has been successfully used in several Mars and Venus missions. The primary focus of the discussion is the techniques employed for landing probes on planets or moons with an atmosphere. Parachutes are commonly used for this purpose to reduce the velocity of the probe after the atmosphere has taken its toll. On the other hand, lithobraking, which happens by crashing the probe deliberately or inadvertently on the surface, requires a robust and sturdy probe capable of surviving the impact. In the realm of science fiction, spaceships travel using a wide array of methods, some of which have scientific reasoning while others are purely fictional, such as anti-gravity, hyperspace travel, warp drive, and spin dizzy.